Welcome. In this video I'd like to go through the various coils that are used in tokamaks and discuss what they're used for and how they fit together, and hopefully try and make sense of the whole machine so you can kind of see how all the pieces fit together. So we're going to go through the main components, which are the toroidal field coils, make the toroidal field, the solenoid which drives the current, and then poloidal field coils which are used for the radial force balance and for positioning the plasma. So when you plot or try and draw tokamaks, we're trying to draw something which has a central axis. So this is called Z, vertical direction. And then everything is essentially symmetric around in this direction. This direction is the toroidal angle. This phi is the toroidal angle. And then we've got a plasma which is approximately a donut shape. So it's a donut which keeps going around in front here. So there's a front part of it in here. So it's a donut which goes around the central axis. And so often when you try and draw this, we'll just take a slice through this right-hand side. So if you want to plot this distance from the axis, from the center here, is R, is the major radius. And so we'll often just plot this as a cross-section. We'll just plot tokamaks as essentially a circle. So this just means a circular plasma which is actually rotated around this axis in the middle. Okay, so that's by way of introducing the coordinate system. So the R, radius, Z, vertical, and then toroidal angle, and the way that we're going to plot the information. So first we have toroidal field coils, so TF coils. So these produce most of the magnetic field. So we have a field which is running around the toroidal direction, which helps stabilize the plasma. And so these are produce the B phi, so this toroidal field, and these are essentially a solenoid wrapped around in a circle. And so if you plot on this kind of RZ plot, so for R and Z, you have the plasma. So the coils have to go through the middle and around the outside. So the TF coils like this. Sometimes they're square shaped, sometimes they're sort of circular or sort of D-shaped, but they have to go through the center of the plasma. So if the plasma is wrapping around this axis here, this limb here goes through the middle, and these will carry a current. So for example, if this current is going up this way, so a current going around in the circuit, that will produce a toroidal field which is going, so P phi, which is into the page. So P phi is going around here. And if you look from the top of the machine, so if this is looking from the side, if you look from the top, so looking down at on the z-axis, what you'd see is that we have a whole set of different coils. So we have coils like this, so around the central axis here. So I have some more in here. And these are arranged symmetrically around here in a circle. So Jet, for example, has 18 of these coils circulate around. Different tokamaks have different numbers of coils. So these will generally produce a magnetic field which goes around in a circle like this. These are producing B phi. Now there's some subtlety of this. If you have too many coils, what happens is you either too expensive and you need to buy lots of coils, and you don't have much space in between the coils to put things like heating systems or diagnostics. But if you don't have enough coils, what happens is you end up with essentially a strong magnetic field near the coils, and then a weak magnetic field in the middle. And so the magnetic field near the coils ends up looking a bit like this. So there's kind of ripple to it, and this is called TF ripple. So some tokamaks, if they have the plasma close to the edge of the coils, so if the plasma gets to large radius near the coils, or if there are not many toroidal field coils, then you can end up with this ripple, and this can lead to particle losses and other effects. Generally a bad thing for confinement. Okay, but as we discussed in previous talks, this field alone is not enough. So we can't just have a toroidal field and confine the plasma. We need other components. And particularly we need a poloidal field which runs in this direction around the machine here. So it runs through the middle of the donut and around the outside. This is the poloidal magnetic field. And in a tokamak, this is produced with a current. So we need to run a current through the plasma. So we want a current going, let's say this way, through the plasma. That's what we call IP, it's plasma current. So you have current drive. So try and drive a current through the plasma in order to produce a magnetic field. So you want to produce a poloidal magnetic field. And so if I draw this diagram here and show how this works. So we have this Z direction with the radial direction, and then we have the plasma. So try and drive a current around here. So we also want a current through here. So you want a current, say IP, often used for plasma current. And now in order to make a plasma current go around here, we need a voltage because the plasma has some resistivity. And so we need a voltage, so V loop is the voltage around the plasma, which is the plasma current times resistance. So it's the electrical resistance of the plasma, and so this is just V equals IR for treating the plasma as a circuit. And so we need to have a voltage. Now the loop voltage is just the integral around a loop, so around this angle in the toroidal direction of the electric field. So E dot dl. So that's just IP times R. This is the V loop, the loop voltage. Now this dl, this is just the toroidal electric field times 2 pi times the major radius. And so this is just the distance around here. Okay, so now we can use the induction equation to work out what this is. So if you remember electromagnetism, we have integral of E dot dl is the integral over the surface of dB by dt over, so this integration over surface. And so if we're driving a current through the plasma, then the loop goes around the plasma, and so the surface goes essentially through, this is S, ds. So if I draw this from the top, it might be easy as well. So if we see from the top, we have so plasma going around here. We have the central axis here. We're driving a plasma current, just going around here, and so we have an electric field. Electric field around here, and so this is the dl. This is dl here. So this loop, and then ds. This surface here is this sort of circle in the middle. And so to drive an electric field around the plasma, we change the magnetic field through the middle, and we do that using a solenoid. So in this picture here, what we do is you have a solenoid through the middle of the plasma. So down the axis here, we have a solenoid, and this produces a magnetic field which is in the vertical direction. So this produces a B field through the middle of the solenoid. So B is going up. So there's a magnetic field in the middle of the solenoid being driven by this current. And now if we integrate across this here, we end up with the magnetic field in the solenoid is part of this flux. And so if we change the magnetic field in the solenoid, we can make this non-zero, so we can change the magnetic field, and this will make an electric field in the plasma. And so essentially it's treating the plasma as a secondary in a transformer. So the primary is the solenoid, and then the plasma is the secondary. So we change the current in the solenoid, and that induces a voltage in the plasma. Note that the magnetic field, which is inside the solenoid, does not directly affect the plasma. So at least if the solenoid is long enough, the plasma is not directly influenced by this magnetic field. The purpose of this magnetic field is just to change in time and drive drive a voltage. So solenoid, so that creates a magnetic field inside the solenoid. So changing current, and that leads to a loop voltage. So it's like a transformer. Okay, so when the plasmas run, this solenoid will typically start charged, and then so it'll start with the current running in one direction, and then it'll ramp continuously down through 0 and then into negative. So the aim of this is to constantly drive a plasma current in the same direction. So for example, we might run, I'll make a plot here of the coil current, solenoid current. This is time. So as the plasma starts up, we want to drive a large voltage in the plasma to break it down and drive a current. And so typically what will happen is we start with a current in the solenoid, then rapidly change the solenoid current. As we change this, we drive a current in the plasma. Once the plasma is warmed up, the resistivity of the plasma drops, and so we just need a smaller plasma voltage to drive the same plasma current. And so this would just be gradually dropped like this. If the power supplies can cope and reverse direction, then once we get to 0, we can switch and drive it in the negative direction. And then eventually it will stop, and then the plasma will terminate. So note that it has to keep going in the same direction with time. It can't go back up, because if we increase the solenoid current again, then we would drive current in the plasma in the opposite direction. And so at some point the plasma would have no current and it would become unstable and hit the wall. So the solenoid current has to constantly change in the same direction. Okay, so there are some limits to this. So clearly there's a maximum current that we can put in the solenoid. So there's some maximum, and similarly there's some kind of minimum current that we can, maximum negative current. So there are some limits to how the range that we can drive, so the maximum currents we can put in the coils. There's also a heating problem, that when you have currents in the coils, they tend to warm up, and the longer you have the currents on, the hotter the coils get. And so there are several limits. There's limits, and the heating goes something like I squared, and then times the time. So I squared is the power dissipated in the coil, goes roughly like the square of the current, and then the time that the coil is running for. And so both of these limit the time that you can drive a plasma this way. And so there are several other coils, and so there are several other mechanisms used to drive currents in plasmas if you want long pulse operation. Okay, so these are the two main ones. So if you have toroidal field, you now have a current driven in the plasma, and so this produces a poloidal field. But there are several other fields we need. In particular, we need coils externally for position control and for radial feedback. So we need a vertical field. And this is needed for radial stability. So if we just have a toroidal field and a plasma current, it turns out this is also not enough. That we need some external coils. So we have again the axis, major radius, the plasma in here. We have a plasma current and a toroidal field going around here. It turns out if you have this, and I'll show in another video that how this happens. Essentially, the plasma will just move outwards due to essentially the pressure force and the force due to its own current, the hoop force and the tie force will essentially drive this plasma outwards, and so you need an additional field to push the plasma inwards. And the way this is done is by having a vertical magnetic field. So we want to make a vertical field like this. So this is BEV. It's a vertical magnetic field. And we do this by making some additional coils. So we put coils out here. And these are both carrying currents in the same direction. So here we want these to carry current into the page. So if these both carry current into the page, they'll both make magnetic field going upwards. And this vertical field will combine with the plasma current. So we have an IP, example of an IP like this. This will produce an inwards force. So this gives us a force inwards. That's the force due to the vertical magnetic field. And this can be used to control the radial position of the plasma. So if we increase the vertical field, it will push the plasma more inwards, decrease it, and it will move the plasma outwards. And this is used for radial position control. So typically there's a feedback system which tries to keep the location of the plasma at a given location. So the operator specifies, I want the edge of the plasma to be at this position. The control system will change the currents in these coils and adjust the vertical field to push the plasma in and out. So in addition to controlling the radial position, you might also want to control the vertical position. So the plasma can be shifted up and down. So here we have the radial field. And so we have a similar picture that in order to control the vertical position of the plasma, we can use a radial magnetic field, and that will push the plasma up and down. So we have R and a Z, and again we have the plasma. Now if you want a radial magnetic field, so now we want a field going like this. It's a little bit more difficult. So what we have to have is again two coils. So we have a coil up here and a coil down here. Except now they carry currents in opposite directions. So if you want so this would be going into the page here, and this is coming out of the page here. And so these produce magnetic fields which look kind of like this, and together they make a magnetic field which is going as we want in the radial direction. So by having two coils in opposite directions, this creates a radial field. Again, combining with the current, the IP. This now makes a force going upwards. So we have a force like this. So we have a force on the plasma which pushes it upwards in this case. And if you want to push the plasma down, just reverse the sign of these two coils. Now in some cases these are combined. So in a minimal set of coils you need essentially two coils for these vertical fields and radial fields, and you just combine the currents together. So the component which is in the same direction produces a vertical field, the component which is in the opposite directions produces a radial field. And so with two coils you can make a combination of radial and vertical field to control the plasma location. So together these are called the poloidal field coils. So these are both poloidal field. These are giant coils, usually the biggest in the tokamaks, which go all the way around the outside of the plasma. And typically there are more than just two, so usually there are more for shaping of the plasma. So we can have a look at an example. So this is a small scale model built at displayed at Monaco a while ago. It's from Wikipedia in this case. You see the photo credit there. But here you can see all the different components we've talked about. So here we have the toroidal field coils. These are these ones here. So you see in the center you have the vacuum vessel where the plasma will sit. The plasma will be here in the middle. These components here, I'll try to draw on here. So this bit around here, this is the toroidal field coil. As it has a kind of a D shape. This is partly because the plasma should be this shape for reasons we'll get into later in the course. Also partly for stresses. So if there's any, if these edges are curved, then for engineering it's easier on the coils. This reduces the stress on the coils. But these you can see all around here. These are coils. There are 18 of them going around the vacuum vessel. So these are the toroidal field coils. These are the TF coils. Then we have the solenoid, and this is actually this chunk in the middle. So this whole thing here is the solenoid. And you see it's an extremely large component of the machine, since a person is about the same size as my cursor here on the screen. So a person is, oh yes, here we go, there's a small person here. Yeah, so the size of a person. So you see this is an extremely large solenoid. There's a very large magnetic field inside, and changing this solenoid is what drives changing the current in this solenoid produces a magnetic field through the middle up here, and by changing that we drive a current through the plasma around here. And then finally there's the poloidal field coils, and these are these ones over here. So you see all of these over here. We have at least 1, 2, 3, 4, 5, 6 around here. And these are providing the vertical magnetic field and the radial magnetic fields for position control. There's also the various shaping of the plasma, which we'll get into, so for producing things like diverters. So this structure down here is for heat handling, so handling the exhaust power and particles from the plasma. And this also requires some kind of control of the plasma shape, and that's provided by these coils down here. Okay, so that's an overview of the coils used in tokamaks. Obviously there are lots of other components, but for now we're just concentrating on the equilibrium and on the coils. I hope that's helped.